In today's video, we're going to take a detailed look at how we can accurately draw ray diagrams for both convex and concave lenses, which are fundamental tools in understanding the behavior of light as it passes through different types of lenses in physics. Let us begin by focusing on concave lenses, also referred to as diverging lenses, because they cause parallel incoming light rays to spread out or diverge away from a central axis. When drawing a ray diagram for a concave lens, we use a specific symbol that includes outward-pointing V-shapes on both ends, which helps to visually represent that concave lenses become wider as you move toward the edges. The next step involves drawing a horizontal line straight through the center of the lens, which we call the axis. We then mark the focal points, which are located on both sides of the lens at equal distances, and you might also hear these referred to as the principal foci, although both terms mean exactly the same thing. Additionally, we place another dot on each side of the lens that is exactly twice as far from the lens as the focal point, and we label these points as 2F. These additional reference points become particularly useful later on when we begin working with convex lenses. It is worth noting that in most exam situations, you will usually be given this entire setup already drawn out for you, so you may not have to construct it yourself from scratch. Now, let us suppose that a cartoon chicken is our object, and we need to draw a ray diagram to identify the precise location where its image will form after light passes through the concave lens. The first step is to select a point near the top of the object and draw two incident rays emanating from that point. One ray should travel parallel to the axis, and the second ray should head directly towards the center of the lens. The ray that travels toward the center of the lens will pass straight through it without any refraction and will continue in a straight path on the other side. However, the first ray, the one moving parallel to the axis, will undergo refraction. In order to determine the correct angle of refraction, we need to draw a virtual ray that appears to originate from the focal point on the same side as the incident ray and passes through the point where the incident ray strikes the lens. This virtual ray is normally drawn as a dashed line between the focal point and the lens and as a solid line after it exits the lens, continuing in a straight path as if it is diverging from the virtual origin point. Once we have drawn both refracted rays, we can find the point where they appear to cross, and this point marks the top of our image. To locate the bottom of the image, we could repeat the entire process, but since the bottom of the object lies directly on the axis, we already know the bottom of the image must lie on the axis as well. This allows us to skip that extra step. As a result, we now know the exact location of the image formed by the lens. In exam settings, once you finish drawing your ray diagram, you might also be asked to describe the characteristics of the image that has been formed. In this case, we would say that the image is virtual, meaning it cannot be projected onto a screen because it is formed by the extensions of diverging rays. It is also upright because it appears the same way up as the original object, and it is smaller than the object, meaning it has been reduced in size. An important point to remember is that with concave lenses, the image will always be virtual, upright, and smaller regardless of the position of the object. Now, let us move on to convex lenses, which are also known as converging lenses. These lenses bring incoming parallel light rays together to focus them onto a single point. Just as we did earlier, we begin by setting up the diagram with the convex lens drawn in place along with the axis, focal points, the object, and two incident rays. The key visual difference is that the V-shapes on the lens symbol now point inward instead of outward, to reflect that convex lenses are narrower at the ends than in the center. As before, the ray that passes through the center of the lens will continue in a straight line and will not be refracted. The ray that travels parallel to the axis, on the other hand, will be refracted and bent so that it passes directly through the focal point on the opposite side of the lens. Once both rays have been drawn, we locate the spot where they intersect and mark that point as the top of our image, perhaps in this case the beak of our cartoon chicken, and draw in the rest of the image accordingly. After drawing the diagram, you may again be required to describe the image. In this example, the image is real because it is formed by actual light rays rather than extensions. It is also inverted, which simply means that it appears upside down in comparison to the original object, and it is smaller than the object in size. Be aware that during an exam, you will most likely be given a simple object, such as an arrow rather than something complex like a chicken. No matter the object, just ensure that you consistently draw your rays from the very top of the object, such as the tip of an arrow, to receive full marks. It is important to recognize that not all ray diagrams for convex lenses will look the same. The diagram we just completed shows an object placed at a distance greater than 2 times the focal length from a lens. If the object were placed exactly at twice the focal length, the resulting image would still be real and inverted but would be exactly the same size as the original object. If the object were placed between 1 and 2 times the focal length, the image would be real, inverted, and larger than the object. The most unusual scenario occurs when the object is placed between the lens and the focal point. In this case, the refracted rays will never converge, so we must trace the rays backward using dashed lines to find where they appear to meet. The image formed in such a situation will be virtual, upright, and magnified, meaning it appears larger than the actual object. And with that, we have covered everything for today's lesson. If you found this explanation helpful and informative, then please do consider giving us a like and subscribing to our channel. We appreciate your time and look forward to seeing you again in another video very soon.